Hello, good morning. Welcome back. You should see the desktop and you should hear me by now. Does everything seem okay?
Yes.
Okay, great. So let me bring up some windows. Okay, now let's see. Let's reassess where we are. Okay, the midterm exam. Oh, where is it? The the midterm exam will be on March 31st. So that's a week from Wednesday. Okay, so the first midterm is a week from Wednesday. The review material for it is, where is it? I'm gonna put I'll move the reminder farther up the page. I forgot where it is now. Um, Here on March 8th. Okay. There's the list of review problems. I'll move that up farther up the page because it's too far down to remember where to find it. Okay. So there's the review problems for the midterm exam. If you have questions about these, please ask me. I'm not gonna, as I said before, I'm not gonna put out an answer sheet for all of them. But if you work on them and you have questions about your solutions, I'll answer any questions about them. And if you work with other people, you can get together and work in a group on these problems. The key is to make sure that you can solve these problems. Okay, so if you have questions about them, please ask. And we're going to continue today the chapter on scheduling. Okay, so we've started chapter 7 on scheduling. Okay, so this is the chapter we're working on now, and we'll do examples today. We're gonna This chapter's got lots of examples like these timelines, and that's what we're going to work on today. We do these timeline examples and see what they tell us about uh, uh, scheduling. Okay, so we're going to do a bunch of timeline examples. That's how we think. This is scheduling theory. There's no code in here. There's nothing in here about the Windows operating system. The stuff about operating systems, real operating systems, will be the next chapter, chapter 8. This is scheduling theory background, the basic idea of scheduling. So, and as we mentioned in class today, the scheduling information here has as much to do with checkout lines at a grocery store as it does to operating systems. It's really scheduling jobs with resources. So, I mean, it includes delivery trucks, checkout lanes, anywhere where people wait in line, anywhere you have somebody. This is actually sometimes referred to as queuing theory. Anywhere where people are getting in a line in a queue, this theory it holds. So this chapter is actually very general. Okay, so that's what we'll do today. Is we're going to do these timeline examples. Okay, let me close these.
Professor, I just have a question.
Sure.
The homework 3, I know it's due March 29th, but it's been
Oh
unavailable. The
no,
page has
it's
been.
yeah. I have yeah. I have not. I still have not had time to put it up. Yeah, the due date will change. Yeah, I
Oh,
haven't had
okay.
time. Yeah, the due date will change. When it's up there, we'll spend it. We'll talk about it. The next program assignment is a pretty complicated one, so I'm getting it ready. When it's up there, we'll spend a pretty good amount of time talking about it. Um,
Okay.
and then the due date, yeah, the due date will have to change because the due date right now is a week from today, right?
Yeah, that's why I was like, oh no.
Yeah, yeah, but we haven't talked about, when it's up there, when it's ready, we'll talk about it in class. As soon as it's ready, we'll be talking about it in class. Okay,
Okay.
so yeah, and
Thank you.
okay, sure. Any other questions about the homeworks that have been due or the exam that's coming up? Anybody got a question about the exam that's coming up?
Will the format be similar to the questions you asked on the review?
Yes. Yeah,
Okay.
very similar kind of problems. You know, um, yeah, similar type problems. Those are the ideas that you have to be able to do. Yeah, the exam's not going to be that long. It'll be about a dozen problems. Okay, so oh, and I got a reading assignment here for you to start reading the next chapter. Okay, which is The multi-level feedback queue is the scheduler that you find in Windows. So that's where we really start talking about specifically the scheduling of in an operating system. Okay. But what's interesting is that this multi-level feedback queue, if you just try to jump straight to it without doing chapter 7 ahead of time, it'd be hard to motivate why the scheduler is so complicated. But it turns out that if you think about it from the right point of view, the scheduler, the multi-level feedback queue scheduler, is actually kind of simple. It's blending two simple ideas from chapter 7. It's going to turn out to be two kind of key ideas in this chapter 7 that when you blend them together in an interesting way, you get this multi-level feedback queue. Okay. So the way the book is written is actually pretty good. It has the disadvantage that you're wondering what the heck the point of chapter 7 is. It doesn't seem to have much to do with operating systems, though it actually another point of view of chapter 7 is a lot of what's in here is historical information. If you go back and look at operating systems in the 60s, or then the scheduling algorithms that are in this chapter 7 actually were used. So one point of view is that it's a little bit of a history lesson in scheduling, but it doesn't pertain directly to modern operating systems. But the other point of view is that if you take a couple of these ideas and blend them together, then you get the modern scheduler. So that's another a good way to think of it. Either you can either is how scheduling used to be done. And there's an old saying that anything that it's worth knowing history because ideas from history keep coming back. So having a sense of how things used to be done is a good idea because it is surprising how often these ideas come back. And in this case, they were blended together to form the multi-level feedback queue for modern operating systems. Okay. All right. So, oh, and then I have these notes up here. This is my kind of outline of the chapter. Okay. So remember, the whole point of scheduling is that we make assumptions, we choose metrics, and we choose an algorithm, and then we analyze. Today we're going to do we're going to do this. We're going to make assumptions, choose metric, choose an algorithm, and do an analysis. The analysis are these timelines. The analysis basically comes down to one of these timelines. This is an analysis of an algorithm using certain assumptions. Okay. So remember, the assumptions are you have a bunch of jobs to do. You know, here the jobs are run this program on a computer. Okay, that's the job. Okay. Now another job might be check out all the items in this shopping cart. Another job could be deliver this package to this address. Another job might be carry a person from one floor to another in an elevator. Those are all scheduling. Those are all scheduling problems. Scheduling elevators, scheduling deliveries, scheduling checkouts. Okay, so our main job is run this program on a computer. Okay, so the word job here, that's a generic term in the world of computing. People refer to these things as jobs. That terminology goes back all the way to the 50s and 60s. People have been referring to these. They could have just as well used the word task or something like that, but for some reason the word job came into play. Okay, so we schedule jobs. Okay, and us a job is run this program on a computer on a CPU. Okay, so here are the questions that we're going to know how long the job takes to do. Okay, something now in the old days of computing, you did. When you ran the payroll program, since you ran it every night, day after day after day, you had a pretty good sense of how long the payroll program would run. If you ran the inventory program, since you ran it every night for every day of the year, you knew pretty much how long it took to run. So it wasn't that unusual to know how long job duration times are. In a grocery store, if you look at somebody's basket, you can make a good sense of how long it's going to take to do it. If you scheduling deliveries, you do know how long you know how far the delivery truck has to drive, so you know how long the job is. The job is due a delivery. You have a good sense of how it is. So this is not now in a computing sense. In a modern computing, as I point out, if I start Word, there's no way in the world to know how long Word is going to run. So this question seems silly in a modern operating system, because you don't have a clue how long a program is going to run. But in a lot of scheduling environments, you do know how long a job is going to run. So that is an important question because you do have a sense in a lot of situations of exactly how long they'll run. And it's going to turn out that question A is going to boil down to really the following question. Is your job going to take a little bit of time or a lot of time? Okay. Are the job duration times known or unknown? When we get to chapter 8, we'll see that that question really boils down to the question, are you presenting a short job or a long job? Is the task short or long? And we can answer that question. Actually, for a lot of computer jobs, it turns out that's all we need to know. Is this something that can be done very quickly, or is it something that can be taken a long time? And then you get a sense that that's an important dichotomy even in a grocery store because they have two checkout lanes, a short checkout lane and a regular checkout lane. There's the 15 item or less line, and then there's the more than 15 item line. Are you small or are you big? So this assumption A is going to boil down to a binary choice of short or long. But the question is, do you know how long a program is going to take? Okay. Do you know when jobs are going to arrive? Okay, we'll start off with they all arrive at the same time. Like in the morning, somebody has a list of jobs that needs to be scheduled during the day. Okay, so that's one thing. Do jobs just arrive as time goes on? Yeah, as the day goes on, as you're computing, do new jobs arrive? Okay. Oh, I'm sorry. That was C. I would misread. Jobs, C is what is the distribution of the job arrival times? When do jobs arrive? Do they arrive all at once? Do they arrive evenly spaced out during the day? This one was uh, related to A. What is the distribution of job duration times? Do you have lots of short jobs and a few long jobs? Do you have lots of long jobs and a few short jobs? Do you have only short jobs? Do you have only long jobs? Okay. Okay. Then here, another one. We'll see as we go along. Can you interrupt a job that's being partially done? Can you just sort of halt a job and switch to another job? The answer is sometimes yes and sometimes no. So, for example, in a grocery store, if you're checking out somebody's basket and it's really a big basket and somebody comes along with a pack of gum, you usually do not interrupt the checkout that's in progress. Okay, it might make sense to just pause that, check out the stick of gum, and then continue with the big basket, but that's usually not done. Okay? So you have this idea that sometimes you're allowed to interrupt what you're doing, and sometimes once you start a job, you complete it. Okay, so that's called preemption. The technical word for that, can you preempt a job? Are are jobs allowed to be halted in the middle of their completion? Yeah, and then you do something else, and then you go back to where you halt when the job that you halted. Okay. Okay. So sometimes preemption is allowable, and sometimes preemption isn't allowable. Okay, another assumption is, are some jobs more important than others? Do you give priorities to them? Okay, that's pretty clear. Are you just going to treat some as more important than others? Okay. Now, actually, there's an interaction between these two. Suppose there is no preemption. Okay, once you're checking out somebody at the checkout line. Okay, and what if you're in the middle of their checking out, you can't stop. But somebody real important comes in. Do you would like to stop and handle the real important person first, but if you don't have preemption, you can't kind of jump to the higher priority job. So these two are a little bit, well, as when we get to them, we'll see that these two kind of go hand in hand. If you're going to allow priorities, you probably want to allow preemption. Okay, so that if something that's more important comes in, you can preempt the less important thing that's being done. Okay, so those kind of go hand in hand. But if you don't allow preemption, then it's a little bit harder to allow for priorities. Okay, now how many resources are there to schedule? Okay, we'll see that in computers, that's things like, does somebody need a CPU? How many CPUs do you have? Okay, that's one. Those are resources. Another possibility is, do you have to schedule CPUs and I/O devices? Like, do you have jobs that need to compute, then they need to do some I/O, then they need to compute again, then they need to do some I/O. So those are various resources: the computer itself, the I/O devices. The CPU itself, do you have more than one of them? Okay, those are assumptions. Like we can assume that we only have one CPU, or we could assume that we have two CPUs. We could assume that none of our jobs need anything but the CPU. Okay. 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 And that's related to this one. Like, do jobs need more than one kind of resource? Okay. So, for example, this would be how many CPUs there are. And then this might be, do jobs need both a CPU and a disk drive? Okay. So if you have only one resource, this is, yeah, there's an issue of how many kinds of resources you have and how many of them you have. So these are two questions related to each other. How many kinds of resources there are, like CPUs and printers and disk drives, and then how many of each resource do you have? Do you have more than one printer? Do you have more than one CPU? Do you have more than one disk drive? Okay, so scheduling needs to know how many kinds of resources there are, and how many kinds of resources there are and how many of each resource there is. Okay. All right. Okay. So those are lots of assumptions that we can make. And we'll be playing around with lots of different versions of these assumptions. Okay. Then we want to measure something. The whole point is to pick something to measure and decide whether we're doing a good job or not. Okay. The two most important measures for us are turnaround time and response time. Turnaround time is, they're defined down here. Like turnaround time is from your arrival time to when you're done. Okay, it's the difference between how long it took you from when you arrived to when you were done. That's your turnaround. Okay, response time is the difference from how long you had to wait when you arrive until you start. Okay, the response time is how long did it take the system to respond to you. So you arrive, you're maybe you're waiting for a while, and then the system starts working on your job. That's response time. So turnaround time is end time minus arrival time, and response time is start time minus arrival time. Okay, so arrival time is when you arrived in line. Start time is when they started checking you out, and then completion time, end time, is when you're done, you're leaving the store. Okay, so you have when you got in line, when they started actually checking you out, and then when you were done. Okay. Turnaround time is from arrival time to completion time, and response time is from arrival time to getting this started. Okay. Later on, we'll talk about some other times, like waiting time is like in the checkout line. Waiting time in our case is going to be all the time you're spent not on the CPU. Okay. In the case of like if you're in a checkout line, waiting time would be from arrival, would be the time would be the same as response time from when you arrived to when you got started. That would be the waiting time. Now, when you're checking out, there is no other waiting. Now, if you were interrupted, if you could be checking out and they could interrupt you and let somebody else use the cash register while you wait and then they go back to your job, that could increase your waiting time. So if you're allowed to interrupt jobs, then when a job is interrupted, that increases its waiting time. Okay, so that the waiting time is kind of related to whether you allow interruptions or not. If you don't allow interruptions, waiting time is just the same thing as response time. Waiting time would be from the time you arrive to the time you start. But if you allow preemption and interruptions, then the waiting time would include the times when you are interrupted. Okay. Okay. Total completion time is the amount of time it takes to get all the work done, not just one job. So total completion time is if somebody has a bunch of things to do, how long is it going to take to do all of them? Okay. CPU utilization is very specific to computers. That means that we'll see later, but when we have more than one resource, like we have both IO and CPU, we could end up having nobody running on the CPU for some reason while things are waiting for IO. So we might not be utilizing the CPU at some point, which is not a good idea. We would like to make sure that we always utilize the CPU. So CPU utilization comes into play when you have more complicated situations where there are more than one kind of resource. There's a CPU and some other resource. And then there's the possibility that you could have things happening on the other resources and there's nothing for the CPU to do. So that's kind of considered bad. You'd like CPU utilization to be 100%, but like in this computer, it's certainly not. Like right now on my laptop, my CPU is probably only being utilized 10 or 15% of its time. There just isn't more work to do. So it if there was more work to do, my computer should start doing it. But if there isn't work to do, then the CPU utilization can be low. Okay. All right. We're not going to actually not going to worry about throughput, and fairness will come up later on when we allow preemption. There's the danger that you could preempt somebody and never get back to them. You know, for example, you're checking out a big basket okay, in the grocery store and you allow preemption, and then all of a sudden 100 people buy a stick of gum. So then you have this, the person who's waiting just keeps waiting and waiting and waiting while lots of little jobs take precedent over it. Okay, if you allow preemption, you could have a problem with fairness. Okay, another possibility is priority. If you allow priority, you could have a problem with fairness. So you have a low priority person who's waiting in line, and it just seems like a never-ending stream of higher priority people come along. And so then the lower priority person can say that they're never going to get a chance. Okay. So priority can give you problems with fairness. You could just have a steady stream of higher priority jobs that block out lower priority jobs. Same thing with preemption. Once you have preemption, you could have problems with fairness. Okay. You could have a shorter job just constantly preempting this one big long job, this big basket that needs to be done. Every time you get started on it, some other person comes along with a stick of gum, and so you have to serve the shorter job. Okay. So fairness can come into play in a couple different ways. Okay. So algorithm in a computer system, that it's actually a real problem. There are real problems with when you get to the more sophisticated computing scheduling algorithms, fairness actually does become an issue because of priority and preemption. It is possible that some job kind of gets stuck with making no what we call progress, either because it's lower priority or either maybe it's a combination. It's a long job with low priority. So it could be interrupted by any short job that comes in. It could be interrupted by any higher priority job that comes in. So the long running, low priority job might feel like it's being treated unfairly. Okay. All right. So those are things we have to measure. The ones that we really matter to us are just these first two: turnaround time and response time. Those are the two measures that are going to be used over and over again in chapter 7 and 8. Okay. And then we have a bunch of algorithms. We'll describe the algorithms as we go through. We'll describe the algorithms by doing examples. Okay, so let's do some examples. Okay, now we do the examples with these timelines. This picture is a little bit funny. If you look at this, this looks like a bar chart, and it's not a bar chart. Let me draw it differently. Let me just show you what I mean by it's not a bar chart. I think here's a better way to draw this. What this oh, what this represents, this is a timeline. Okay, so it represents a timeline. Okay, so there's a timeline. Okay, and I'll mark it off and say, you know, there's like time 0, say 10, and unit of time doesn't really matter. So it's just a timeline marked off in, say, units. So this is 0, 10, 20, 30. Okay, now the height of this means nothing. What's important here is the letter A, B, and C. So what we're going to do is we're going to say that in this time interval from 0 to 10, we're running job A. That's all he really meant to say. And in this time span from 10 to 20, we're running a job that's called B. Okay. The height of this doesn't mean anything. I mean, he drew these bars. It would really, it just, when we do these like on a chalkboard, it's simple enough to do it just like this. This represents the idea that job A is running from 0 to 10, then from 10 to 20, job B is running, and from 20 to 30, job C is running. Okay, that's all that really means. Okay, so he went from 0 to 10, 10 to 20, and 20. He didn't put the 10 and the 30 timeline in there. Okay, it's not a bar chart. It's really just a timeline where you denote which process is running for each interval time. Now, what we have here are assumptions. We are assuming that we know the job duration times. Okay, so what we know that we have a 10-second job A, a 10-second job B, and a 10-second job C. So we know that the arrival times, the arrival time assumption is that all the jobs arrive at the same time. So we're assuming that somebody gave us A, B, and C to run. Okay. So we ran, and we only have one CPU. So so A is put on the CPU, and there's no preemption. So the assumptions are listed here. There's only one CPU. This is the textbook's starting point. So for example, if you go back over here in the textbook, here's his assumptions. Okay. So there's the assumptions he's going to use for a little while. Okay. So the assumptions are, here's another way to write them. I wrote them down here. Okay. So we're assuming that we start with three processes. We start with three jobs, A, B, and C. They all take 10 units of time, and we can't interrupt them. There's only one CPU to use. So we run one until it's done, then we run the other one till it's done, then we run the other one till it's done. The question here is, what's the turnaround time, and what's the response time, and what is the okay? So let's, like, for A's turnaround time is 10, and for B's turnaround time is 20, because B waited for 10 and then got to start at 10 and ran till 20. So so A's turnaround time is 10, B's turnaround time is 20, and C's turnaround time is 30. Okay, that means that the average turnaround time is going to be 10 plus 20 plus 30 divided by 3. Okay, you just compute the average. Okay, so that's the average turnaround time. So you just add up their each one has a turnaround time, and the average would just be add them up and divide by 3. Okay, so that's an example of a calculation. Okay, now response time, you could do the response time for A is 0, response time for B is 10, response time for C is 20. So then you could go down here, you can compute you could also compute an average. An average response time is, in this case, is going to be 0 plus 10 plus 20 divided by 3. Okay. The arithmetic in these problems is simple, but we'll see as we go along that we can get some interesting results. I mean, the calculations are real trivial. If you want to find the average response time or the average turnaround time, you find the turnaround time or response time of each job, and then just add them up and divide by how many jobs there are to get the average. Okay. Okay. So this is an example of choosing the scheduling algorithm we're using here is essentially what's called first come, first serve. Okay, we assume that A, B, and C arrived at the same time, so we just essentially just randomly pick one to do, just give them an order. Yeah. So as the book points out, we're assuming they arrive at the same time, but we're doing first come, first serve. So that's kind of a bit of contradiction. So what we're really doing is we're just randomly giving them an order. Here, the order was A, B, C, run A, then run B, then run C. Okay. So it's first come, first serve with no preemption, okay, and 1 CPU. Okay. And then we can compute the average turnaround time and average response time. Okay. Now that's this example here. It's just a warm-up example to get a sense of what's going on. Okay. Now let's make it a little bit more interesting. Instead of having A be a 10-second job and B be a 10-second job and C being a 10-second job, make things a little bit interesting. Make a 100 time unit job. Okay. Make A be 100. So what we just did was 10, 10, 10. Okay. Okay. Let's do, let me just say that. Let's do another one. Let's change it to be 110, 10. Okay. So let's see, how do I create a new file? Oh, okay. So let me just draw. Okay, so now we're going to do A is 100 units of time, B is 10 units of time, and C is 10 units of time. Okay. And we're going to assume that A arrived first. Okay. So we're going to assume that A arrived first. So we'll start by running A. Okay, A is going to go out here to time 100. Okay, and then here will be B. B will run from 100 to 110, and C will run from 110 to 120. Okay, so this will be time 0. Okay, and then at time 100, we can start. So we're running A all this time, run B this time, and run C this time. Okay, and this would be 110, and then 120. Okay. All right. Now let's do some little calculations. Let's do turnaround time. Okay. So the average turnaround time. The average turnaround time. Okay. A's turnaround time is 100. B's turnaround time is 110. And C's turnaround time is 120. Divide by 3. And let's see. Can I do that in my head?
110.
Yeah. So the average is 110. Okay. Okay. Yeah, the average, because you're averaging these three numbers here, so the average is right in the middle. Okay. Now, this was using first come, first serve. So this is the algorithm first come, first serve, or first in, first out. There's different names for it. Now let's try different ordering. Make the ordering BCA. Okay, so make the ordering BCA. So now we'll run B first. Oops. Run B. Run C. Then run A. Okay, the time, start at time 0. This will be time 10. This will be time 20. And then over here at 120 is when we're done. Okay, right. Now let's compute the average turnaround time. Okay, so the turnaround time for B is 10. The turnaround time for C is 20. And the turnaround time for A is 120. And we get a much better, point is we get a much better turnaround time. Notice that what this has done is it's essentially done like what in a grocery store where there's, if you do the shorter jobs first, there's an advantage to it. B and C are much happier in this way of doing things. Okay, now what is the average? It actually turns out to be what? 50? Yeah, the average turnaround. See, the average turnaround time is way better on average. Now, A is probably a little bit less happy. B and C are way happier, and the average turnaround time is improved. It's more than cut in half. Okay, so this is called shortest job first. Okay, this is a scheduling algorithm. The scheduling algorithm, shortest job first, says put the shortest job. The assumption are still that we're starting with these assumptions here. There's only one CPU. All jobs arrive at the same time. Once a job is started, it runs to completion. There's no other resources, and we know ahead of time each job's duration time. So we have all these restrictions here. But now we can say, well, which algorithm should we use if we care about response time? Okay, so we're not changing any of these assumptions, but we're saying, well, you could schedule them first come, first serve, or you could schedule them by looking at their completion times and saying, oh, let's put the shortest one first. Okay. If you do that, shortest job first will always give you better turnaround time. Okay. So we have this idea that there is an algorithm that will optimize this one metric, that if we have all other things considered equal, if we use shortest job first, we get a better turnaround time than, for example, if we use first come, first serve. Okay. Now, we don't have many other algorithm choices. We can't, there aren't any, well, another algorithm we could do is longest job first, but that's exactly what we did here. First come, first serve also happened to be longest job first. And in that case, it didn't give us a good turnaround time. Doing your long jobs first isn't going to, is probably not a really great idea because, it makes short jobs wait too long. Okay. All right. Now, in the old days, when computers were scheduled like grocery store lines, in the old days, they didn't have modern operating systems, so they ran jobs one at a time on a computer. They would do things like this. They would run the short jobs first so they could just get them out of the way and let the longest jobs run later. And you just get a better average turnaround time that way. Okay, so now here's a problem though. Let's change this a little bit. Okay, so now let's relax an assumption. Okay? Instead of having all the jobs arrive at the same time, let's suppose the jobs arrive at different times. Okay, so let's suppose, let me do another. Let's have job A have 100 its a duration is 100 and its arrival is time 0. Okay, so we're going to give now we're going to relax the assumption that everybody arrives at the same time. Okay, so A has a duration of 100 and 0 is the arrival time. Okay, and then job B, it'll have a 10 duration and an arrival time of say 10, and we'll have a job C, which has a duration of 10 and an arrival time, say, of 10. Okay. Now, how are we going to schedule these? Okay. If we schedule them at time 0, there's only one job to schedule. So at time 0, we're back to where we were before, kind of like we're back to doing longest job first. At time 0, there's nobody to schedule but A, so we have to run job A first. Okay. Now at time 10, these other jobs arrive, but if we're not see, I remember one of our assumptions was we don't preempt anything. Okay, so if we're not going to preempt anything, A is going to run all the way till time 100. And even if we're using the shortest job first algorithm, we don't have any leeway here. Okay, so our algorithm is shortest job first. So let's say that our algorithm is shortest job first, but the jobs can arrive at different times. In this case, shortest job first doesn't help us much because we're still stuck running. If by bad luck, a really long job arrived first, okay, then when the short jobs arrive, they have to do nothing but wait until this one's completed. So we're stuck with essentially this bad schedule of having to wait until the long job is done before we can run the short jobs. Okay, so then we would run B and C like this. Okay, all right. So if we relax one of our now, so a minute ago we said the shortest job first is good. It gives us a good response time. Gives us good average response time. But that was assuming that everybody arrived at the same time, so we could pick the short jobs. So we could pick the short job out of the long job and run the short job first. If we relax an assumption like everybody arrives at the same time, now we're kind of stuck with a bad situation where if a long job arrives first, we have to run the long job. Now, if the long job and the short job arrive at the same time, we'd pick the short job first, and we would run the short job first. But for example, if we change this so that A and B both arrive at time 0 and C arrives at time 10, well, we would run B first, then A, then C, but C would still be stuck waiting. Okay, so if we change this a little bit to, for example, if we changed it to B had 10 duration, but 0 arrival, okay, then we could improve things a little bit. In that case, it would look like this. Since we're using shortest job first at time 0, we would run A, or I'm sorry, we'd run B, then we would run A to here, and then but then C would still be stuck waiting a long time. So now it would look like this, run B, because B and A arrived at the same time. So shortest job first says pick B, run B, then run A, but then C still had to wait till, C still had to wait a long time. Okay. So what we want to do is kind of make this a little bit, we want to improve, we want something that will improve this algorithm. Okay. Right. So shortest job first is great for response time, for turnaround time, if everybody arrives at the same time. You can just pick, let me say this. You can just pick the shortest job. You can pick the shortest job. But if you don't have any preemption and you allow arrival times be different, then shortest job first doesn't do you much good, because you don't know when you schedule this long job, you don't know that there's two short jobs about to appear. And since you can't interrupt this, you pretty much have to let this one run and then run the two short jobs. Okay, so this gives us a bad average turnaround time. This one gives us a little bit better average turnaround time, but because we had A and B arriving at the same time, so we could pick B to run first and then run A, but C, it arrived at this time here. This was C arrived at time 10, but didn't get run till over here. Okay, so what we're going to do is modify the algorithm a little bit to account for situations like this. Okay, So we're going to switch to another, I want to keep that picture, but draw another one. Yeah, draw another one to compare it with. Okay. So let's look at, here's what we'll do. We'll, suppose that A has a 100 duration, okay, and a time 0 arrival time. Okay. And we're going to go back to, and B is going to have a 10 duration and a time 10 arrival time. Okay, and let's see, what should we do about I'll give C an arrival time of, say, 30. Okay. Okay. Now the algorithm is going to be something called shortest time to completion first. Okay, that's going to be the algorithm. Shortest time to completion first. It needs to allow preemption. We need to allow preemption. Okay, and if we allow preemption, we can do better than we were doing over here. So this is our third scheduling algorithm. Our first scheduling algorithm was first come, first serve. Our second scheduling algorithm was shortest job first. Now this is our third scheduling algorithm, shortest time to completion first. It wants to improve on shortest job first, but solve this little problem here, that if you have different arrival times, shortest job first won't do you any good, because once you launch a long running job, you can't interrupt it. So we allow preemption, and now here's what the algorithm is going to be. Let me the algorithm now is that you always schedule the job that has the least amount of work left to do. Okay, that's a little bit tricky to explain. The shortest time to completion first. Okay, so let's go through and see what would happen here. Okay, so at time 0, we only have one job to schedule, so that's A. So we start running job A. But then at time 10, somebody arrives. Oops. At time 10, a new job arrives. Now that means we have to decide now, we have to make a scheduling decision. Should we stick with A, or should we go to the next job? At time 10, A has 90 seconds left of work left. B's got 10 seconds of work to do. So B has the shorter time to completion. So that means that we should switch to B. So we switch to B, and B will run until time 20. Because that's when it finished. At time 20, it finishes. Okay, now we have to schedule someone. Well, the only one left, the only one that's running is A, because C hasn't arrived yet. So we go back to running A. So we'll go back to running A. See, notice we've allowed an interruption. We've allowed a preemption. B preempted A. The short job preempted the longer job. Okay. And then at B, A will now at time 30, we say there's an event, a scheduling event. The scheduling event is that C arrives, okay? So C arrives at time 30, so we have to make a scheduling decision. So there's a scheduling event, and we have to make a scheduling decision. So at time 30, well, actually, I can put it down here. At time 30, C arrives, okay? And over here, at time 10, we have the event that B arrives, okay? When B arrives, since it was only a 10-second job, we went ahead and scheduled it. When C arrives, it's a 10-second job, so we go ahead and schedule it, okay? And so and then at time 40, C will be done. Oops. At time 40, C will be done. And so then we go back here and we schedule A, and A will run all the way up to it completes, and A will finish out here at what? This will be
120.
120. Okay. Now, B and C have good response times. Okay. The response time for B is, uh, what's, oh, we should, let's compare what's, over here. We want to compare this one up here with this one down here. Okay. This one up here was, well, no, they were actually a little bit different because C had, it doesn't really, the arrival time of 30 didn't really matter here. Okay. B and if you think about this one, B and C get these really long response times because they arrived at time 10, but they didn't like B arrived at time 10 and had to wait 90 seconds, and C arrived at time 10 and had to wait 110 seconds. So they had really long time that they had to wait. So their turnaround times are pretty bad. Okay, so the turnaround time here, the average turnaround time is just a little bit more than 100. Okay? The average turnaround time here is going to be real short because B's turnaround time, well, is only its turnaround time is its runtime. See, its turnaround time is from the time it arrives to the time it ends, and that's just 10. Same with C, from the time it arrives to the time it ends. And A's turnaround time isn't that much worse than if it was over here. See, its turnaround time was from here to here. Now it's from here to here. If you notice that C actually did, I'm sorry, A didn't really get affected that much by this. B and C are helped a lot by this, and A isn't really hurt very much by this. Okay, so this is actually this is a big improvement over shortest job first. Now, grocery stores can't do this one. Grocery stores do shortest job first by giving you by having two checkout lanes. Okay, they do shortest job first by having a checkout lane for small items and a regular checkout lane. This one will require in a grocery store you to actually let a cashier stop checking somebody out, pause their checkout, check out somebody else, then go back to checking out the long job. Then somebody else arrives and you stop checking out this one and you start checking out this one. You can't do that in a grocery store. Okay, so grocery stores don't have anything like shortest time to completion first, but it's actually a very good algorithm in terms of real computer scheduling. This is a very good algorithm, but it requires this extra idea of preemption. And so that means you have to have this idea that when a job arrives, we consider that a scheduling event. When a scheduling event happens, we make a choice of who do we schedule now. So at first, at time 0, we had A arriving. At time 0, A arrived, so we just schedule A. There wasn't anybody else to schedule. Then at time 10, B arrives, so we can choose, do we stick with A or do we go with B? Okay. Now, for example, in this one, I could have a C. Let's suppose we put, like in this one, suppose we had a job D with, say, a 50 duration time. And give it an arrival time of, say, time 80. Okay. Now, if I add this one to the timeline, then I would have down here, I would have at time 80, I'd have a scheduling event. So this would be time 80. Okay. Now what happens here? At time 80, I have a scheduling event. Okay. Oh, so the scheduling event is that D arrives. Okay. Now D needs 50 units of time, but at that point, A has 40 units of time left. Okay. So A has 40 units of time left at that point. Okay. So we would continue writing A. So now we would put up here that A continues, but we still made a scheduling decision. At this point here, 80, we made a choice to stick with A because A had 40 units of time left. And then now here, after A completes, then we would run D. And D would run all the way out here till 170. The important thing is here is that there still is a scheduling decision made here. And the scheduling decision is somebody arrived, so we have to decide who should be running now. So we make which one has the shortest time to completion. Well, since A only needs 40 more units of time, but D needs 50 units of time, A is the shorter one, so go ahead and let A complete here. A got preempted here and here because A was the longer job. So at this scheduling point, A got, we say, preempted by B because A still had 90 units of time left and B needed only 10. Okay. Then A ran a little bit more. Now A's got 80 units of time left. C needs 10, so A gets preempted. Okay. Then A runs for 40 more units there. So A got 10 units of time here, 10 units of time here, 40 units of time there. So it's run for 60 and it's got 40 left. Okay. And D comes along that needs 50. So at this point, when D arrives, well, A only has 40 left. D needs 50. So A is the shortest time to completion. Okay. Now notice how to do this algorithm, you have to know exactly how much time everything takes. Okay. Now remember, if I run Word, no one knows how long I'm going to be running Word for. But this isn't unreasonable in some situations. Like in a checkout situation, you can look at how many items there are. If you're scheduling, say, truck deliveries, you know how long each delivery is going to take because you can pretty much see where the truck is and where it has to go to. So there are situations where you would know how long a job is. Okay. Shortest time to completion says that when there's a scheduling event, which usually is when somebody arrives, the scheduling events can be when somebody arrives or somebody ends. For example, this is a scheduling event here because B ended. And this is a scheduling event here because A ended. Now, there wasn't any, I'm sorry. This is a scheduling event because B arrives. This is a scheduling event because B ends. This is a scheduling event because C arrives. This is a scheduling event because C ends. This is a scheduling event because D arrives. This is a scheduling event because A ends. And then there's nothing left here. Okay. So a scheduling event can be either when something ends or something arrives. And at each scheduling event, we decide who to run next, based on shortest time to completion first. But that means we have to know exactly how much time every job takes, which in some situations is reasonable, in some situations isn't reasonable. But this one gives us good turnaround times, just like shortest job first did. Okay. This will give us better turnaround times than, well, this gives us better turnaround times than shortest job first. If we were doing shortest job first here, let's see. Well, shortest job first doesn't have any preemption. So shortest job first would just run A until it was done. Yeah, if we did this example here, if we did shortest job first, we can do that down below. So suppose we actually did shortest job first. Now, shortest job first doesn't allow preemption. Okay, so at the beginning, there's only one job to schedule, and it's A. So A goes all the way out to 100. Okay. Now at time 100, oh, but you still have these, you do have B arrives here and C arrives here. But you can't interrupt A, so you're just running A all this time. So you're running A, you're running A, and you're running A, okay? Even though down here we have B arrives, and over here we have C arrives, okay? Now, when A ends over here, this is time 100. When A ends, now we can make a scheduling choice. Now B and C, now I gave them the same duration time. I probably should have made one of them a little bit different. Since they are the shortest jobs, at this point we would just schedule, they both have the same amount of time, so we could schedule out here to at time 80, I should put that in. At time 80, D arrives. So when A ends, when A ends, we have a choice of three jobs: A, B, B, C, and D. B, C, and D. Now B and C are both shorter than D. So at time 100, when A finally ends, we can schedule, say, B. We would schedule B, and then after that, we have another. When B ends, we have to choose between C and D, but C is shorter. So we would then schedule C. Okay. And then finally, we would run D. Okay. The timelines aren't lining up very well. Okay. But then we would finally run D. Okay. Now, each of these is a scheduling opportunity. But since we can't preempt A, when B arrives, we just notice that B arrives, so we keep running A. Then C arrives, we can't preempt A, so we keep running A. Then D arrives, but we have to keep running A. Then when A is done, now we can use shortest job first, and we say, okay, we have B, C, and D to run. Well, B and C are the shortest, so we just give them an arbitrary order. Do B, then do C, and then do D afterwards. Okay, and we'll still be done at the same time here. We'll still be done at time 170 here. Okay, all right. So shortest time to completion first. Now, if you actually work this all out, you'd find out that this gives you a better average turnaround time, okay, than this one. Let's see, can we do the calculations? They're a little bit tedious to do. The average turnaround time for shortest time to completion first will be, okay, what's the turnaround time for A? He started at time 0 and he ended at time 120. So his turnaround time is 120. What about B? He started at time 10 and ended at time 20, so his turnaround time is 10. Okay. C started at time 30, ended at time 40, so his turnaround time is 10. Okay. And D started at 120. No, D arrived at 80 and finished at 170, so his turnaround time is 90. Okay. And then we would divide that by 4. Okay, so you could do the arithmetic. Anybody? Anybody do that in their head? So that's 140, 230. What's 230 divided by 4? It's about 58.
57.5.
Okay. Okay. Now, what about down here? Do I have room to do the calculation for the other one? Well, I'll do it on the side. Okay. What about for here? Shortest job first. Let's do the average turnaround time. Okay. All right. Now, A arrives at time 0 and is done at time 100. So his turnaround is 100. Okay. Now, what about B? B arrived at time 10 and was done at time 110. So his turnaround time is 100. What about C? C arrived at time 30 and was done at 120. So its turnaround time is 90. Okay. And D arrived at time 80. Oh, D's turnaround time is the same because it's still going to arrive at time 80 and end at 170. So it's also 90. Okay. Now, what's that turnaround? The turnaround time now is close to it. Notice that the turnaround time, let's see, it's 100 plus 100 plus 90 plus 90. So it's just a little bit under 100. What is it? Let's see. What's 380 divided by 4? 95? I think 95. Okay. Okay. So the average turnaround time, so this one was average. This one was average turnaround for shortest time to completion first. Okay. And this calculation over here is average turnaround for shortest job first. Okay. So shortest time to completion first gives you a better average turnaround. These are a little bit tedious calculations. We do a couple of examples like this, and the intuition is that doing short jobs first is better. Okay, shortest job first by itself is a good idea, but it doesn't allow for preemption. So basically, you just take shortest job first and allow preemption. But then you're looking at the shortest amount of time left to do. Okay, so now when you allow preemption, you don't say which is the shorter job, you say which is the shorter one left. So that came up over here with time when D arrived here, D's a shorter job than A. D's a 50-second job and A is a 100. But at that point, A doesn't have much left to do. The shortest time to completion of A was less than the shortest time to completion of D. Okay, so you take the idea of shortest job first. Let the short jobs go first. That's a good idea. But then when you allow interruption, preemption, you have to change the terminology a little bit. It's no longer, are you a short job? It's, oh, how much time do you have left to do? So we do whichever job has the least amount of time left, that's what we switch to. Okay. All right. So at this point, save that. at this point, at that point, we've relaxed several of our assumptions. Okay. There's still only one CPU. We're no longer assuming that jobs arrive at the same time. We're no longer assuming no preempt. We're allowing jobs to arrive at any time. We're allowing jobs to be preempted, but we still are using only one resource. Okay, and we know how much time. So we've relaxed 2 and 3, and kept 1, 4, and 5. Okay, so we've relaxed. See, so we've done shortest job to completion needs to relax 2 and 3. Okay. Okay. Now, the next thing to do, we're out of time, is switch to a different metric. What we've been doing was we've been emphasizing turnaround time. The next thing is to emphasize our other important metric, which was response time. Okay, and we'll see that there's an algorithm that optimizes response time. Okay, but it'll do bad for turnaround time. Okay, so we're going to switch now to response time, find an algorithm that gives us good response time, average response time, but it'll go back to being bad for turnaround time. And there's going to be there's a tension between these two things here. You cannot get good turnaround time and good response time. And the resolving that tension is what ends up being the next chapter, the multi-level feedback queue. Okay, where it's going to blend the algorithm that gives us good turnaround time and the algorithm that gives us good response time. We're going to blend those two algorithms to give us a modern scheduling algorithm. The algorithm that gives us good turnaround time is shortest time to completion first. Okay, so we've got to this algorithm, shortest time to completion first. It gives us good turnaround time. We've eliminated a couple of assumptions and we get good turnaround time, but we're still getting really bad response times. Then we'll find an algorithm called round robin that'll give us really good response times, but it'll be bad turnaround times. And then we'll try to figure out how to blend those. Okay, so we'll do more examples on Wednesday like we've just been doing. We've gotten up through this shortest job first example. We've done examples up to shortest job first, or shortest time to completion first. Okay, then see, we want to do this, a new metric. So we're up to here, 7.6. So now on Wednesday, we'll introduce the response time and see that what we need to do is switch to this. Well, this algorithm here will give us good response time. Okay, anybody got a question? We run out of time. Any question? Okay, so on Wednesday, we'll do more of these timeline examples, and we'll see that those will give us a sense of what it is we're trying to, the time, when you do these timeline examples, that's where you build a sense of like what these algorithms do to the metric. That's what we're really asking is, given a metric like average turnaround time, what does the choice of algorithm do to the metric? Okay, and shortest time to completion first is going to give us way better. Oh, and a shortest job first is going to be better than first come first serve. Okay, so right now we have 3 algorithms: shortest time completion first, shortest job first, and first come first serve. And they just, each one is better than the other. First come first serve would be the worst. Okay, so we'll go ahead and quit there. And okay, remember, if you have questions about the review problems for the exam, please send me an email or come to office hours. Okay, so I'll go ahead and end sharing here, and we'll meet again on Wednesday. Bye.